Okay, based on some questions I've had over the last couple of days, I just wanted to give a couple of tips that might be helpful. When you are looking at a graph, we know that obviously this identifies a first order reaction based on the fact that it is the natural log of H2O2 versus time, and we get a straight line. But then we ask, okay, well, how do we find K? So if you remember right, we have our equation that aligns with this graph. And this equation, it's written on the back of our equation sheet like this. Natural log of the concentration of A at time t minus the natural log of the concentration of A at time 0 is equal to negative KT. So there's our K right there. Now you might wonder, how does this equation align with this graph? Well, let's just rearrange it really quickly. We get the natural log of A at time t is equal to negative KT plus the natural log of A at time 0. So hopefully you can see right now, we have essentially a line equation, y equals mx plus b. So here's our y-intercept, here is our y value, and here is our slope. Our slope is going to be negative k. So right down here. So we can write down here, negative k equals our slope. So then we just wonder, what is our slope? We can just quickly map that out. Here we have our rise is -2, our run is 18, so -2 over 18 is equal to negative k. So then k would be equal to 1 over 9. And then what would the units be? Well, we can figure out the units just based on our standard rate law. We know that the rate for a first order equation is equal to k multiplied by the concentration of x to the first. And we can just put in put numbers in there, or just units instead of actual numbers. And we know that the concentration of X is measured in molarity, and then K will have as our unknown, and then the rate is going to be molarity per second. And so we just divide both sides by molarity, and we're going to get 1 over seconds is equal to K in the case of a first order rate. And so in this case, then K would be seconds -1. So K is equal to 1 over 9, seconds -1 is equal to K. And this would then be our K for that graph. As we look down at the bottom, we have another situation where in this case, we don't have, notice it's not like the natural log over here, and we don't have a straight line. So we might be asked, what is K for this? Or we might be asked, what is the half-life? Okay, and so there's different questions that you might ask. So we look at this and we say, okay, we have to try to figure out what's the rate order. And in this case, we can figure it out by looking at the graph, only because it's first order rate. And the way we know that is we want to look at consistent time segments and to see how long it takes for half of the reactant to disappear. So we go from 2 down to 1, and that took 4 seconds. Okay, then we do another 4 seconds, and that went from 1 down to 0.5. So we had half of it there. That was another 4 seconds. Let's just check one more just to make sure. We went from 0.5 to about 0.25 there in another 4 seconds. So it's very clear that we have a half-life of 4 seconds. So we can use the back of our equation sheet, and we have this equation, t to the 1/2 equals 0.693 divided by k. And so now what we can do is we can solve for k to figure out what k is for this. So we take 4 equals 0.693 over k, solve for k, and we're going to get k equals 0.693 over 4, and that is 0.173. And of course, it's first order, so it's going to be 1 over seconds is the unit. Now, let's take this, and then we might have another question that says, how long does it take for 99% to decompose? Okay, this is a little bit of a different question. So what we can do is we can use our integrated rate law, which for first order reactions is going to be the natural log of A at time t minus the natural log of A at time 0 is equal to negative KT. So all we need to do is we just need to say, okay, we've got 99% decomposes. So what you can do is you can just use percentages instead of your concentrations. And the reason it's okay to use the percentages is because really what we're talking about here is just proportionality. If we start with 100 and end at 1, we can start with 1 and end at 0.01. All that matters is that we end with 1% left based on where we start. So what we can do is we can just say, I mean, the simple thing is to just say A sub 0 is 100 and A sub t is 1. And so if we substitute those in, natural log of, and I'll just put those in and do the math here, and then we'll go over it. So I've substituted the numbers in here. Natural log of 1 minus natural log of 100 equals negative 0.173 t. And then we're just going to solve for t, and I'll do that on my calculator and come back to you. Okay, after I do that math, combine these two terms and then divide by negative 0.173, I get 26.6 seconds. And it's a little tricky to say how many significant figures there are because really up here, we're using different values. And so it's difficult to say this is different from just one significant figure. So I'm going to keep 3 significant figures for this purpose, but I could even make a note that it technically has 1 significant figure. So the last thing I would do is I would just go up here and look at this and say, okay, does that make sense when we look at our graph? Does it look like at about 26 seconds there'd be 1% left? And we can see that it makes pretty good sense that we would be about there. We can also do even just divide by 2, several times just to get that estimate to say, does that answer make sense? And in this case, it does make sense that at about 26.6 seconds, you would have about 1% remaining of our reactant. Let me know if you have any questions on that, but I just noticed that would probably be helpful, and maybe even on some of the multiple choice, this information might be valuable. Hope you have a great night. Talk to you later.